Every major railway disaster forced engineers to confront a simple truth. One broken part, one ignored warning, one unsafe practice can change railway safety forever. Railway safety rarely improves in calm. It improves after tragedy. Across more than a century, 5 catastrophes each exposed a hidden weakness, and each one forced the railways to change. This is the story of what failed and what we learned. In the 1870s, the Tay Bridge was a wonder of its age. Nearly 2 miles long, it carried trains across a wide Scottish estuary that had only ever been crossed by ferry, a symbol of Victorian ambition. Then came the night of December 28, 1879. A violent winter gale tore down the Firth of Tay. As a train moved onto the high central spans, the bridge gave way beneath it, and the train plunged into the freezing water below. Everyone aboard was lost. Around 75 people died, and not one passenger survived. When divers reached the wreck, they found the carriages still sealed. The storm had given no one a chance. The inquiry was damning. The cast iron was brittle and badly cast. The bracing holding the structure together was too weak, and the design had barely accounted for the force of the wind. So Britain rewrote the rules. Bridges would now be built to survive real wind loads, with a safety margin 4 times over. The new Tay Bridge, and the Great Forth Bridge beside it, set a standard of caution that still echoes today. 1917. The First World War was grinding through Europe, and the railways were under enormous strain. In the French Alps, a train was prepared to carry soldiers home on leave, down a long and dangerously steep mountain line. It was massively overloaded. More than 1,000 men were packed aboard wooden carriages, pulled by a single locomotive where 2 were standard. The brakes simply weren't built for that much weight, on that much slope. The driver knew it. He warned that the train could not be safely controlled. But under wartime pressure, a transport officer overruled him and ordered it down the mountain anyway. On the descent, the brakes began to fail. The train accelerated out of control, faster and faster, until it derailed at tremendous speed and tore itself apart. As many as 700 people were killed, still the deadliest railway disaster in French history. The lesson was written in tragedy. Steep routes need their own strict limits, and an engineer's warning must never be overruled by the pressure to keep moving. June 1981. In the Indian state of Bihar, a passenger train was crossing a bridge over the Bagmati River. It was monsoon season. The train was severely overcrowded, and the river below ran swollen and fierce. As the train crossed, it derailed, and carriages plunged from the bridge into the Bagmati River. In moments, hundreds of people were trapped beneath the water. It is the deadliest rail accident in India's history. The official toll was 235, but the true number is almost certainly far higher. Estimates climb past 800, with many victims never recovered from the river. Bihar forced hard questions about overcrowding, about how much weight a train and a bridge can safely bear, and about running through dangerous weather. It pushed India toward better load management and stronger monitoring of its bridges. June 1989, in the Soviet Union, near the city of Ufa. This disaster was different because the danger wasn't on the train at all. It was hiding beside the tracks. A nearby pipeline carrying liquefied gas had been damaged years earlier, and it had been leaking. Heavier than air, the gas pooled in a low valley along the railway, forming a vast, invisible, flammable cloud. In the dark, 2 crowded passenger trains entered the valley from opposite directions. As they passed each other, a single spark, most likely from the overhead lines, ignited the cloud. The explosion was immense, its force compared to a small nuclear blast. Around 575 people were killed, and many of them were children, traveling for the summer holidays. Ufa changed how the world thought about railway safety. The threat wasn't only the train, or even the track. It was everything in the corridor around it. Railways and pipeline operators could no longer afford to ignore one another. June 3, 1998. The railways had entered the high-speed age. Germany's gleaming ICE train was a point of national pride, racing across the country at 200 kilometers an hour. But inside one of its wheels, a tiny fatigue crack had been quietly growing. To cut weight and noise, the wheel wrapped a steel tire around a rubber-cushioned core, a design never fully tested at high speed. The signs were there. Passengers had complained of strange noises and vibration. An onboard computer had even flagged the wheel, but the warnings were not acted on in time. At full speed, the steel tire finally shattered. A fragment caught a switch in the track, threw the train from the rails, and drove it into the pillars of a road bridge, which collapsed onto the carriages below. 101 people died. Eskid forced high-speed rail to grow up. The resilient wheels were abandoned for solid, one-piece designs. Ultrasonic crack testing and strict tracking of every component's life became non-negotiable. Set side by side, the human cost is staggering and uneven. These were never just accidents. Each one was a system failing in its own particular way. And yet, look closely, and the same villains appear again and again. Brittle materials, thin safety margins, warnings that went unheard, and the pressure to keep running when something was clearly wrong. But trace the century forward, and a hopeful pattern emerges. Each disaster left its mark on the rulebook. Wind loading, braking, crowding, corridors, wheels. Step by step, failure by failure, the railway taught itself to be safe. Railway safety does not improve because accidents are forgotten. It improves because each disaster forces engineers to redesign the system, so the same failure becomes harder and harder to ever repeat.